I'm sure many of you already know or know of Dr. Jeannette Wing, who is currently the Executive VP of Research at Columbia University and also Professor of Computer Science there. She has had a distinguished career and very broad experience, both as an academic, a professor, a corporate executive, a former director of the National Science Foundation, professor and head of computer science at CMU, as well as the head of all of global research at Microsoft, MSR. She's a fellow of too many associations for me to list all here today. She has made seminal contributions in the areas of computational, computability and computational thinking. Jeannette looks very young, but we chatted and she completed her PhD at MIT CSAIL while Rodney Brooks was still there. Okay. So when we first met a while ago, we chatted about our shared academic and corporate backgrounds and so on. And then we started to go over our overlapping, circles of friends and colleagues. And I noticed that Dr. Wing had been at Microsoft as a head of research. So I asked her, so how well do you know, and how well do you know Qi Lu, who was at one point, for I think a span of 6-7 years, president of Online Services Division there. And Jeannette said, know him. I was on his PhD committee. So if you know Qi Lu at all as a friend, you would know that his doctorate there was a seminal, a transformative life event for her. For him, sorry. So as for me, among Dr. Wing's many accomplishments, that ranks as one of the greatest. So it's my great honor and pleasure to introduce you, Professor Jeannette Wing, whose main research interests today are in the area of trustworthy AI.
So I'm going to talk about trustworthy AI, and also thank you for that introduction. I can share with the audience a lot of Qi Lu stories if you want, but let me get on with my talk. So as Chris mentioned, I have been promoting this new research direction for the community, which I call Trustworthy AI. So let me just give you the motivation for what I'm talking about. And some of this beginning will be a little tried and true, but it sets up the context. So as we know, for certain tasks, AI systems have achieved good enough performance to be deployed in our streets, in our homes, for example, recognizing objects or speech, and even exceeding human performance, such as playing Go and other games. The promise of AI is huge. They will drive our cars, they will help doctors diagnose disease more accurately, they will help judges make more consistent court decisions, they will help employers hire more suitable job candidates. However, we are discovering that these AI systems can be brittle and unfair. Adding graffiti to a stop sign fools the classifier into saying it is not a stop sign. Adding noise to an image of a benign skin lesion fools the classifier into saying it is malignant. The media and academia showed how a risk assessment tool used in US courts is racially biased. The media showed that Amazon's AI recruiting tool was biased against women. So how can then we deliver on the promise of the benefits of AI, but address these scenarios that have life-critical consequences for people and society? In short, how can we achieve trustworthy AI? And I know for this particular audience, you're interested in the safety critical systems like self-driving cars and other kind of transportation systems where AI plays an important and futuristic role. So what my comments are going to be with respect to trustworthy AI are especially germane to safety critical systems. So let me put into context where I'm coming from. I started 20 years or more ago following and being a part of the Trustworthy Computing community. And over and the National Science Foundation, the National Academies, Microsoft, and academia, of course, have been involved in promoting trustworthy computing for decades. Trustworthiness for computing systems has come to mean reliability, does it do the right thing? Safety, does it do no harm? Security, how vulnerable is the system to attack? Privacy, does it protect a person's identity and data? Availability, is the system up when I need to access it? And usability, can a human actually use the system easily? And by computing, I mean, of course, hardware and software components of a system, but also people. From trustworthy computing to trustworthy AI, we're really upping the ante in terms of the properties we care about, the trustworthiness properties we care about the system. Of course, we care about the trustworthiness properties from trustworthy computing, reliability, safety, security, and so on. But with AI systems, we have to add new properties, new trustworthiness properties of interest: accuracy, robustness, fairness, accountability, transparency, and so on. And for AI, we're talking about data and, say, a machine learned model plus the task at hand. All of this is running on a computing system. So for accuracy, how well does the AI system do on new unseen data compared to data on which it was trained and tested? Robustness, how sensitive is the outcome to a change in the input? Fairness, are the outcomes unbiased? Accountability, who or what is responsible for the outcome? Transparency, is it clear to an external observer how the system's outcome was produced? Interpretability, explainability, can the system's outcome be justified with an explanation that a human can understand and or that is meaningful to the end user? And then ethical, was the data collected in an ethical manner? Will the outcome be used in an ethical manner? And so on. These properties I list on this slide are new to consider for the trustworthy computing community. And they are emerging because of the AI systems that we're building and deploying today. So how can we achieve trustworthy AI? I set up the context for what I mean by trustworthy AI through the properties of trustworthiness that AI systems demand. For the rest of the talk, I'm going to talk about only one approach towards how we can achieve trustworthy AI. I want to emphasize this is one approach of many complementary approaches, as we have already been using in software engineering and building computing systems in industry and so on. And this is yet another approach that has had decades of fundamental research that is being deployed in industry today, especially for safety and security applications. So let me start with the context of traditional formal methods or traditional formal verification. You see in this red rectangle the expression M satisfies P. That's how to read that. Here, M stands for a piece of code, a program. It could be a protocol. It could be an abstract model of a concurrent or distributed system. The double turnstile is a mathematical symbol that's read as satisfies. And it basically stands for the logic and tools, for instance, model checkers, theorem provers, SMT solvers that have been used in computing, in trustworthy computing and informal methods for many years now to actually prove very formally that a property is satisfied by a model M. And then P finally is the way in which we express the property of interest. We usually express this property of interest in terms of some kind of logic, usually a Boolean logic or temporal logic. And we have studied the kinds of properties, especially for concurrent and distributed systems, again, for decades, to the point where we know very well how to classify some of these correctness properties in terms of what's called safety properties and liveness properties. So I am really promoting trustworthy AI using a formal methods approach based on decades of advancement in research and development on what we have been able to do for using formal methods for trustworthy computing. So from traditional formal verification, one last thing, and sometimes in this expression M satisfies P, we add explicitly an E, so a fourth component to the expression, where E stands for the environment of the system that is modeled by M. So it, in particular for a concurrent system, E might be everything but the system that we care about. Or another way to think about it is if M is a piece of code, E could be the operating system, the compiler. And for self-driving car, E is the physical environment that the car is driving in. So I just wanted to say that, as I mentioned, we've made much progress in formal methods for concurrent and distributed systems, for trustworthiness properties like safety, security, and so on. And probably the most well-known method for formally verifying a system to be correct is one called model checking. This was invented in the 1980s. This is a very simplistic view of what model checking is. You have two inputs. One is a finite state machine model of the M of the system that you care about. The second is the expression of the property P written in some kind of temporal logic. And then people have built black boxes that are model checkers that run algorithmically based through the behaviors represented by model M, the finite state machine, to ensure that the property P holds. And the model checker outputs one of two answers. One could be yes, every behavior represented by the finite state machine model M satisfies the property P, or it outputs no, and very usefully, it outputs a counterexample. It outputs a behavior that is an example of where the property P is falsified. So this technique has been around for many years. It's been studied for many years. It's now used in industry all over the place. Now, what about AI systems? How are we upping the ante for verifying AI systems? How are we upping the ante in using formal methods to verify AI systems? So analogous to what we have on the left-hand side, which is my expression for using formal methods for verifying trustworthiness properties of computing systems, we have on the right-hand side a reinterpretation of what M satisfies P means. First of all, M could be a high-level model that we've learned through machine learning. It could be a DNN in particular. But don't forget, M is, in the end, still a piece of code. It's not a piece of code that a human wrote. It's a piece of code that the machine wrote. But it's still a piece of code. It's a piece of code that no human would probably ever write. It's a very complex set of if-then-else statements with interesting conditions on each of those if statements. And that is basically traversing that, say, DNN. So M can be quite complicated. It's not usually human readable. It's something a machine produced. Satisfies is interesting because the double turnstile now has to appeal to not just Boolean logics, but likely probabilistic logics. It may also require reasoning about reals. For instance, using interval analysis to reason about intervals of real numbers. And P, the property P that we care about, itself might be expressed in terms of a probabilistic logic. So P, it might be an expression over probabilities or stochastic processes, and so on. What's most interesting in reinterpreting M satisfies P in the AI context is what E might be. And in particular, I'm going to use D to stand for a model of the data used to train M, the data used that we expect M to work on when deployed. And it might be modeled in terms of a stochastic process or distribution that what we want is that would generate data inputs on which we want M's outputs to be verified. So this captures the essence of my talk. D, M satisfies P. It's a formal expression of how to think about verifying an AI system using formal methods with respect to trustworthiness properties. Now, this is basically a futuristic vision of what we'd like to be able to do. And we're just scratching the surface at making progress at answering this question, given a set of data or given classes of data distributions, given a machine learned model, does it satisfy a trustworthiness property like robustness or fairness? So in the remainder of my talk, I'm going to pick apart each of these DM satisfies P and explain what the research challenges are and where we are in some of these challenges. I want to emphasize the two main differences between reasoning about an AI system with respect to the trustworthiness properties I mentioned and reasoning about, say, a typical computing system and reasoning about safety and security and reliability. The first main difference is the need for probabilistic reasoning. And I'm going to talk more about that in my next slide. The second main difference is the role of data. The more traditional question of collecting and partitioning the data for training and versus testing, specifying unseen data is a brand new research question. What do we quantify over is a pretty technical question, which I'll touch upon. And then how do we do the verification? So the need for probabilistic reasoning. M, remember, think of it as a DNN. Think of it as a machine learned model. M is semantically and structurally different from a typical computer program. It's inherently probabilistic. Internally, the model itself operates over probabilities and outputs results with assigned probabilities. This is not like your typical computer program. Structurally, M is machine generated, as I mentioned, and unlikely to be human readable. In some sense, it's another kind of intermediate code, which gives me great hope that techniques from programming languages that are very good at analyzing intermediate code, static analysis, dynamic analysis, and so on, could be applicable to analyzing the internal structure of machine learned models M. Certainly to scale in a way that humans cannot. And finally, inherently, when we are putting M in some environment, we need to reason about the uncertainty of M's environment. And the only way in which we know mathematically to reason about uncertainty is through probabilistic reasoning. Now that's just M that's motivating why we need probabilistic reasoning. P itself may be formulated over continuous, not just discrete domains, and or using expressions from probability and statistics. So for example, robustness properties for DNNs are characterized as predicates over continuous variables. Fairness properties are characterized in terms of expectations with respect to a loss function over reals. And differential privacy, which is the only formal notion of privacy that has been bandied about for a decade or more already, is defined in terms of a difference in probabilities with respect to a small real value. So reasoning about probability, or the need for probabilistic reasoning, is unavoidable. And finally, when we look at the logics for determining whether M satisfies P, we may need to appeal to probabilistic logics or hybrid logics. And the good news is that we have such logics. And what we need to look at for the future in terms of research is the need to scale or invent new techniques that work over reals, nonlinear functions, probability distributions, stochastic processes, and so on. Just to give you a glimmer of hope in terms of probabilistic logics and hybrid logics, probably, again, decades ago, was the first that Tom Hensinger, at the time at UC Berkeley, invented hybrid automata. This was a picture from his PhD thesis, where he talked about an automaton that represents a thermostat, where in the circles, which represent states, you can express the state of the thermostat in terms of differential equations. And then you have these Boolean jump conditions that take you from one state to the other. And that's why it's hybrid, because you've got Boolean conditions that take you from one state to the other, but within the state, you're reasoning about continuous variables. So that's basically all this says. And since his PhD thesis, there have been many, many tools that allow one to reason about these kinds of automata. So one can reason about continuous variables and Boolean variables in the same breath. Now, there's another technique invented by my former colleague when I was at Carnegie Mellon, Andre Plotzer, called differential dynamic logic, which within the same logic, so you don't have to use Boolean logic for reasoning about one part of the automata and non-discrete logic for another, but in the same logic, you can reason about both continuous and Boolean variables. So for instance, you could write a program, this is the top line, where you can express the behavior of functions, typical discrete assignments, x gets f of x, or differentials, x prime gets some f of x and some other condition. And then you can also express the property of interest, P, in terms of some kind of logic, where you can, as in traditional temporal logic, talk about for all runs or for some run. And again, much work has been done, books have been written, tools have been built, and applications, in particular for this audience of interest, have been in the cyber-physical system space, where Andre has looked at ensuring that cars don't collide, airplanes don't collide, and there's a smooth handoff when trains and so on pass satellite towers. So that gives me some hope that there are some logics out there that can help us reason about inherent probabilistic properties and models of AI systems. Also, in reasoning about uncertainty, there have been, besides probabilistic and hybrid automata, there have been model checkers. Those are tools I mentioned before that support probabilistic reasoning, probabilistic logics, and even probabilistic programming. So there are programming languages out there that have been invented. This is a little snippet from a programming language that kind of looks like C, but it adds random variables, C1 and C2, where you flip a coin and you make an observation as you're running the program. So either C1 or C2 will be the value that you're observing. So that is probabilistic reasoning. Now I want to talk about the role of data, D, in this expression DM satisfies P. And let me first make a distinction between available data, data at hand used for training and testing, and unseen data, data over which M needs or is expected to operate without having seen it before. So there's the standard problem in machine learning where you have a lot of data, you're collecting a lot of data, and you want to partition the data. How do you partition it between training and testing? And then the only interesting verification question we might ask is, what guarantees can we make of this partition with respect to a desired property P in building a model M? More interestingly, suppose we actually do a verification, DM satisfies P, and we find that it doesn't hold, then do we need to collect more data? How much data actually suffices to build a model M for a given property P? And then it may depend on the kind of property we care about, whether we're trying to verify against robustness or fairness. And then what new kinds of data needs to be collected if the property doesn't hold. Now, here's actually a brand new problem for the formal methods community. And it really arose after I tried to apply my formal methods thinking towards this verification question of AI systems for trustworthiness properties for AI. And the question is, how do we specify unseen data, that part of D in this expression that we haven't seen yet, but we know we're going to want to test and deploy M on, and it's got to work. So the question is, how do we specify the data and or characterize the properties of the data? We could specify D as a stochastic process or data distribution via its parameters. This is a very standard process, a standard method that we know from statistics. So you specify the mean and variance, or mean and standard deviation, and we already have two parameters that basically give us the distribution for a normal distribution. We could specify the distribution or the stochastic model in terms of probabilistic programming languages. Perhaps the most well-known and well-used probabilistic programming language is STAN, and it's used to specify statistical models. So it's very applicable. It's applicable to a wide class of models, but it's only for certain kinds of statistical models and applications. But in reality, we have large real-world data sets that do not fit common statistical models, or which have thousands and thousands of parameters, where one wouldn't write a program necessarily on our own to try to specify. That's the whole idea of machine learning, to learn those parameters. So there is an issue of, and so we don't have an answer to this. You know, we don't have a way to specify these kinds of large real-world data sets. You know, it's an open question. There's another interesting research conundrum that I encountered in thinking about this, which is what I call breaking the circular reasoning. So to specify unseen data, we need to make certain assumptions about the unseen data. That's like to specify anything. We always need to make certain assumptions. Now, one can question, would those assumptions not then be the very same as those we would need to build the model M in the first place? We're kind of pushing the problem away from, okay, how can we trust M, to now, how can we trust the specification of D? So how do you break this circular reasoning? One idea is to use a repertoire of statistical tools, which is completely outside the realm of verification and formal methods, and to break this reasoning. Another that's more in the realm of computing is assume that an initial specification is small or simple enough that we can eyeball it and check it manually. And then we use what's called in the formal methods community an iterative refinement process. And this is a very common process that we use in verification. It's basically a counterexample guided abstraction refinement, where you try to prove something, you get a counterexample, so then you refine your abstraction, and then you try again to prove it, and hopefully this process converges. So that's a conundrum that is an open question. And then there's also the question of specifying unseen data. How does the specification of unseen data relate to the specification of the data on which M was trained and tested? So there's another interesting question that arose when I was thinking about what does it mean to verify an AI system with respect to trustworthiness property. And that is the question of what do we quantify over? In traditional formal methods, we strive to prove a very strong statement for all x p of x. So for all values of a variable x in my program, p holds. For all executions of a concurrent or distributed system, p holds. A very strong property, to the point where you're overproving what you need to prove with respect to what you actually might deploy. Now, what about AI systems? The problem with AI systems is we do not expect M to work for all input data, or for all data sets D, or for all data distributions D. So what we can try to do is characterize a class of data distributions for which we can strive to prove P holds. So the question of what do we quantify over may very well depend on the property P we care about. So for example, for robustness, in the adversarial machine learning setting, we might want to show that M is robust to all norm-bounded perturbations D. So that is a class of D over which we would prove M is robust, where robust is our property P, and we're given some M, say a D and N, over which we can prove once and for all norm-bounded perturbations D, that property of robustness holds. But more interestingly, we might want to show M is robust to all semantic or structural perturbations for the task at hand. So consider computer vision, where we know it's very easy to add noise to a picture, and the classifier will misclassify the picture. For instance, in this case, thinking a panda is a given. So this is thinking these are completely different animals, and the classifier can be very easily fooled. And the reason I say task at hand is consider trying to put a computer vision system on your self-driving car. And you obviously you're driving in the road, you want it to recognize cars in front of you, but you want it to be robust with respect to a dent in the fender of the car in front of you, because it's still a car. It just might have a dent in the fender. So you still want your classifier to say it's a car. On the other hand, if you're taking your car into a repair shop, then you want your vision system to distinguish between a good, perfect fender and a dented fender. So that's where not is it only property dependent, but it may be task dependent. As another example of what of pondering the question of what do we quantify over, and that it might be property dependent, let's also now consider the property of fairness. So some colleagues of mine at Columbia and I wrote a paper a few years ago on the trade-off in some sense between robustness and fairness. And what we found was for fairness, we might want to show that a machine learned model is fair in a given data set, and all unseen data sets that are similar for some notion of similar. What we found was when we used the canonical data sets that are out there, and we built the fairest classifier possible, what we did was we very slightly reweighted the coefficients and the parameters in the data distributions, and we easily made a fair classifier unfair. And you can see that what the red and the blue bars show is that the differences in the parameters are so, they're basically very subtle. There's almost no difference. So that is basically saying fair classifiers can be brittle. So in this paper, what we showed was to use an online algorithm, pretty standard approach, a two-player game algorithm, to build a fair classifier that is also robust, but in particular robust to a class of distributions. So not just one distribution, but to distributions that are similar. So now let me turn to the verification task, which is the double turnstile. And the questions are, the open research questions are, how do we check available data for desired properties? For example, if we wanted to check whether a data set is fair or not, what should we be checking about the data set? If we detect that the property does not hold, how do we fix the model, amend the property, or decide what new data to collect for retraining? And what is the equivalent of a counterexample in the verification of a machine learned model? And how do we use it? We know how to do that for concurrent and distributed systems where we use model checking as our verification technique. What is the analogy for AI systems? And how do we exploit the explicit specification of unseen data, the D in my expression, to aid in the verification task? This is analogous to having an explicit E environment that is specified when trying to verify, say, a concurrent system with respect to a property. And then how can we extend existing and standard verification techniques to operate over data distributions, perhaps taking advantage of the ways in which we formally specify unseen data? So these are all open research questions. I want to give you, again, a glimmer of hope. There's a technique that my colleagues here at Columbia have been pursuing called interval analysis. And it's a way to propagate bounds with symbolic intervals. And it works very efficiently over DNNs. And it's a sound over approximation. And at the time of publication, because it's highly parallelizable, it's over 200 times faster than at the time the state-of-the-art SMT solvers. And it has been applied to cyber-physical systems, the kind of systems you care about. I'm not going to go through that technique in detail. I wanted to pop up a level and say the particular method approach that I've been talking about for formal methods has been very heavy on verification, which I would call post hoc verification. You have an M, you have a P, you have a logic, you have a data, a set of data, and then you do this verification. One can think about different ways of approaching ensuring that a machine learning model satisfies a trustworthiness property. First of all, you might want to take into consideration the tasks that might make the verification problem easier. Second, in a correct by construction approach, it's not a post hoc verification that one does, but it's building the model to be correct, to satisfy that trustworthy property by the way in which you construct it. So there's no verification needed. Some other opportunities and outstanding challenges is compositionality. Obviously, what we'd like is to verify pieces of a system, put the pieces together, and know that the verification that we've done of a particular property on each piece still holds. And then finally, as I mentioned earlier, there are statistical methods for model evaluation and model checking that the computer science community may be less aware of. And these techniques combined with formal methods and verification techniques might be very promising. So let me just give you an example of what I mean by correct by construction. And I'll do it in the context of privacy. So this is, again, some, actually, I'll do it in the context of robustness, but you'll see where the privacy comes in. This is, again, some work done by my colleagues here at Columbia. So we all know the problem of DNNs being brittle. As I mentioned earlier, you put some duct tape on a stop sign and the DNN misclassifies it. So a solution which is inspired by differential privacy is to add a layer of noise in the DNN. And you can control this noise that you add. And you can also control where you add it so that you can guarantee that the classifier, the DNN, will be robust within some range of perturbations to the input. And it is using the kind of guarantees that differential privacy gives you when you're trying to ensure that some data set satisfies the differential privacy property. So I'm going to close. This is my characterization of what it means for trustworthy AI to meet formal methods. DM satisfies P. Thank you very much.
Thank you, Jeannette. Any questions? I'll start with one. So this is actually probably, if not the first and one of the few presentations that I've attended that talks about trustworthy AI from the perspective of formal methods. And I think more generally, because of industry, taking on machine learning and so on, and commercializing it so quickly, my observation is that a lot of us, and myself included, but certainly there's a lot of talk about trustworthy AI from a very intuitive level. And it's kind of like, my trusted system is going to be very different from yours because that's the way I feel like it. Where do you see, it's not just formal methods, but just more rigorous methods, more rigorous systems, coming from research, working in academia. Yesterday, we had a speaker who was a lead product manager for Michelangelo at Uber, and they care very much, no matter how you feel about the company, but they actually care very much about privacy and regulations and so on. But they're also bumbling around. What can you give us a sense of what you see from your perspective, how this is sort of disseminated or osmotically growing as a movement, both in academia as well as industry? to adopt these methods?
Okay, it's a great question, and I'll be very, I think I can be comprehensive in my answer. First of all, I wrote this paper only a couple of years ago. 2021, it came out. It was really my call to arms to bring together three communities: the AI community, the security and trustworthy computing community, and the formal methods community. Now, the security and trustworthy computing community are very familiar with formal methods. They don't do everything in terms of it, but they do a lot. The formal methods community has been very, very successful, especially in industry, for safety critical and life critical systems, which is why I think it's important for your community, self-driving car community, if you will, cyber physical systems community more generally, to at least know that these sorts of techniques exist and they are being used in companies like Amazon and Microsoft and hardware companies like Intel and IBM and so on. These are major companies. That's on the one hand. Now, these techniques are not prevalently used or pervasively used in companies because for the most part, you don't need the kind of rigor and formal guarantee that these kinds of techniques can provide. Unless, of course, you care about human life. And I think you do care about human life. And that's why there's a whole, I would say, couple decades now of research in the whole area called cyber physical systems. It's a program that I started when I was at the National Science Foundation in 2007, 2008. There's a whole academic community. And one of the techniques that they look at are verification techniques like the ones I've talked about. So if your community is interested or unfamiliar with what these kinds of verification techniques can do to at least help assure you that the devices you're building are safe and secure and so on, then it's something worth looking into. The challenge are these AI systems. What I see are the challenge. AI systems, if you buy my argument that they're inherently probabilistic, we're in a whole different world of logical reasoning. And computer science has, up until modulo AI, computer science has been very lucky. It's all been about black and white, true or false, on or off, 0 or 1. And now these AI systems are forcing us to reason about probabilities and stochastic processes and stuff that we never used to have to think about, let alone the kinds of properties. I mean, I would say of robustness and fairness and so on. Fairness is really, really hard. Robustness, I think we could get our hands around, which is quite relevant to your community. That's what you really care about, robustness. Of course, companies like Uber and even other companies in the CPS space may also care about fairness, but first and foremost, you care about I think robustness. You just don't want to make any mistakes and you want your system to be reliable. So I think my suggestion to your community, which is moving very fast and maybe doesn't have the time to learn these techniques or learn the underlying mathematics and technical details and tools behind these techniques. I think minimally you need to be aware that they exist. You may want to partner with academia and or industrial labs that know these techniques, that have built tools to scale. But I think you have to at least be aware. Now, I can say that if you go and you use your intuition to bless something trustworthy, it's a little dangerous because people's lives depend on these systems. And one of the open secrets is that there's a lot of promise of using AI in healthcare. But the reality of it is not a lot of sophisticated AI is used in healthcare because doctors are making decisions about people. And not until we can really trust those AI systems about the quote decisions they're spitting out, not until the doctors can trust them, let alone the patients, are we really going to see AI take off in the healthcare industry. Yet the promise is huge. And so there's where, I put my optimist hat on and say, we have so much to offer, but we have also to be cautious. And we definitely, as technologists, we have to be careful about what we're promising. We have to be very clear about what this system can do and what the system cannot do and what we don't know about the system.
Yes, thank you, Professor Jeannette Wing. One of the things that you proposed in this talk, which is the qualification or evaluation of models over clearly stated data domains, helped me resolve my feeling for a long time now why I'm very uncomfortable with models that don't come with confidence scores over a data set on which it performs some inference, right? So there has been, usually when developers of AI models build models, they try to classify over 5, 10 label classes, and then the model is going to be programmed to identify the classes closest to the situation at hand. But given the need for safety and robustness, do you think that we should require all models to say whether the model itself is familiar with or comfortable with interpreting a certain data case at hand, right? Should the model be allowed to make any recommendation at all?
I think you got one of my points. And you said it in a way that makes more sense to a practitioner than the way I said it. But I think if someone's trying to sell you a model and they're promising all sorts of things, including confidence scores, you can say, well, what data does this work on? And if they say anything, everything, well, then you should be suspicious. But then you can ask, they won't say that if they're not a true snake oil salesman. They'll say it works for this particular data set, then that's also an honest answer. It might not be very interesting, but it's an honest answer. And then you can say, well, is there a class of data sets like this data set that it also might work on? And then you can have a technical conversation about the similarities of those data sets or the data distributions and the confidence scores associated with each of those classes of data or each of those classes of data distributions. So the separation between the model itself and the data already is kind of an intellectual breakthrough, but it gives you the vocabulary or a way to think about how to ask questions to someone who's trying to sell you a model. So you got it.
Yeah, I feel like the transition from software engineering to AI is sort of analogous to, when classical physics met quantum physics, and we're here in Copenhagen trying to figure out what is the right interpretation.
Fantastic talk, by the way. The first time, as Christopher said, we've seen a formal approach being recommended for a very difficult question about AI. So in my role at Automatic, actually, I end up talking to a lot of customers and listening to what they're saying. And most of our customers are cyber physical. They're industrial people. They make physical things. And I should ask you, I hear euphemism in the same problem stated in different ways. It's about, can I trust this AI? Humans are going to be consuming the output of these AI. How do we know the answers are correct? So it's all the same thing, I think, and I believe you're exposing an approach and a system to go do this in a formal way where you can objectively answer. And I think most of our customers would benefit from this. So my question for you was, I somehow felt you're underselling what you've actually developed here. And I was wondering if, you're a person of your stature, should we have a national policy around this driven from the political side around safety and agenda, and say these formal methods are required for anybody who's offering systems that are going to be concerned about it? And let me give you a simple example. It is not as complex as healthcare. I was talking to one of the nation's leading water purification company. This is basic stuff, and their simple question is, how do I know that your process optimization recommendations for producing pure water meets the standards that we are held to? I mean, it's as basic as that. If we could give them an answer that says, here, we can tell you exactly what this AI is going to do in a formal or a way that people understand it, I think it would just drive the adoption. So I actually think that, so my question was really, do you think we should really be doing more around policy and really kind of come at it from all angles, not just academia and industry? Industry wants something, but they are never the people who create these things. It comes from research and formal thinking, right? So
Well, thank you for your encouragement and your support. And now I want to be very realistic with you. These techniques have been around for decades. I got my PhD thesis talking about this kind of work. And has been in my lifetime that I have seen these techniques adopted by companies, but for certain kinds of systems where reasoning about, say, a consensus protocol for a distributed system, let's say Paxos, is so complicated, yet so much of the companies, like compute servers, rely on the correctness of the implementation of that algorithm. They will use these formal techniques to do the verification, or they will use these formal techniques for proving deadlock freedom of a particular, say, database or something like that, where it's so critical to the bottom line of the company that they will pull all the guns out. For traditional run-of-the-mill software, these techniques are not used. It's usually testing, simulation, and so on. And so as much as I would love to wave the formal methods flag and say, you must, in order to ensure the customer's request, I also understand the challenges, not the technical challenges, but the challenges of more widespread deployment. Now that's just for typical computing systems. Now we're trying to address AI systems. The AI community is not at all familiar with these techniques, on the one hand, and the formal methods community is just beginning to dip their toes in the AI waters. So as much as I'd love to say, I've got an off-the-shelf formal methods technique that will work on a DNN that's going to be in your vision system in some cyber physical system, I don't have that. It is about research right now. Now, the glimmer of hope I have is that AI has moved so quickly that we do have White House reports. We have the National Institute of Standards and Technology, NIST reports, that come close to stating these kinds of policies you're asking for. They don't mandate the use of formal methods, but they do say more work needs to be done in formal verification of AI systems for properties like robustness and fairness. So they are making these statements, but the technology, the research still has to be done to the point where we have the off-the-shelf tools to use for proving robustness or fairness of an AI system, much in the way we already have off-the-shelf tools to prove deadlock freedom or some other safety or liveness property of a concurrent or distributed system. So that is state of the art.
Yeah, my additional observation on Nanda's question is that in the last 6 months alone, I've sat at 3-4 different types of tables. The governmental table, the university table, Harvard Kennedy School, of course, a lot of technical tables and so on. And I think Dr. Wing is exactly right. People have been working on these things for 10, 20, 30 years, but they're not sitting at the same tables, right? And particularly with AI being adopted so quickly in industry, there's not a lot of time for these conversations. But certainly NIST has been trying to get more industry perspective, perhaps can use more from academia. But I think this symposium is I think later on we'll have conversations, some roundtables where we do have that diverse set of experiences brought to the same set of same place. So I look forward to that. Is there any more questions? Okay, one last one.
Dr. Wing, it was a great talk. So this, it's more an observation, and I want to hear your thoughts on this. It's a continuation of what we are just discussing here. So it's coming from the formal approaches that you're talking about, more from robustness, and you brought up NIST. I was listening in on some of the talks at NIST earlier, and I have a couple of other examples as well, where they were listing out these frameworks for trustworthy AI and discussing, okay, we need to get to the table and at least agree on these frameworks and these formal approaches before it starts rolling out into actual implementations. And of course, that is a bit away right now. And there was this one defense person at the table who basically shut that discussion down from the perspective of, yes, we will try this out and it sounds really great, but in enterprise type of scenarios, not in life-threatening mission operations where you're going to be asking your AI to make critical decisions. And we also heard a talk yesterday from a leader in the medical AI space, where he was talking about robustness within models, but from the perspective of we will have to live with the differences in the data sets that you get, physicians' understanding of the data. So putting these formal approaches in there is something that is way into the future, not something that we can expect to see a tangible or concrete implementation anytime soon. I'm just curious, from your perspective, where do you see this actually going from a formal framework and the research that's needed to first agree upon this, and then to put it into something that truly works, not in the trivial sense like the defense guy talked about, or I'll just put it in some enterprise setting where I don't care what happens, to something that actually is truly life critical?
First of all, I unfortunately do agree that it's going to be a long term. It's a long-term vision. I'm probably known for stating these things that don't get realized for many years. Again, I can say that although formal methods had been talked about, formal verification had been talked about for software systems and hardware systems in the 1980s, not until circa 2002 did these techniques come together to show, in particular at Microsoft, their use in industry. And just to be concrete, there was a project called the SLAM project, and I happened to be on sabbatical at Microsoft at the time, where they brought together these techniques. They built a system that mere mortals could use, and they helped Microsoft reduce the device driver problem. So for those of you around, I mean, maybe some of you weren't even born then, but around that time, Microsoft used to get blamed for a lot of blue screens of death because of third-party device drivers. So they knew they had a business problem to solve, even though they weren't responsible for the code. And it's using these techniques that I talked about, which really was a tipping point for the company. And that was just the start of industry strength formal methods. That was easily 2 decades after these ideas of formal methods were emerging from academia. So I don't want to say we have to wait 20 years, but I do want to say I am just now starting to talk about this problem, and we probably don't want to have to wait 20 years, but it's going to take a while, to be honest, because I've already seen how long it's taken for traditional software, let alone AI systems.
Because this symposium is special in the sense that every person in this room is working on some life-critical system or another, which is an unusual gathering of people compared to the usual conference that I attend. So I want to be optimistic, and hopefully we can invite
I
Dr.
do
Wing
want to
back.
end on an optimistic note, and that is to remind everyone that the federal government, I mentioned the White House, there are agencies like NIST, NSF is pumping money into this problem. Research is as I speak, working on this issue. The difference between, I'd say, the 80s and now is that AI systems are already being deployed. They are out there, and there is really no good reason for us to trust them. So if they are making life-critical decisions, I can only hope that the users understand the uncertainties associated with the outcomes that these systems are predicting. So Chris, I want to be optimistic too. I'm ever the optimist.
Exactly.
But I
so I
do
want to invite
think
you.
I do think we should all be very. We should question the customer or the client, if they're or someone who's trying to sell us something. But we can also start learning some of these techniques and using them for the systems that you're building yourselves.
Yeah, maybe we'll invite you back next year and compare notes and see how fast the industry has or has not moved. Right.
All right.
All right. So
Thank you very
thank you
much.
so much.
Okay. Bye-bye.